Okay, so yesterday we talked about reaction mechanisms where we have several elementary steps, okay, that when add up to an overall balanced reaction. We also learned that the rate determining step is always going to be the slowest step, so that the reaction can only proceed as fast as the slowest step. Okay, so in this case, let's look at we have 3 different elementary steps, so I'm going to just number them just for my own sake. That's what I do. Okay, so what is the rate determining step? All right, well, it's always going to be the slowest. So it's going to be number 2. Okay, and this is going to be our rate determining step, meaning we are going to use that step to get our rate law. Okay, are there intermediates? Okay, now we got to be careful. Intermediates are produced and consumed in the reaction. Okay, so first of all, let me just get the overall reaction. Okay, I don't know if it asks us for it, but let's just get the overall reaction. Okay, let's circle anything that's on both sides. So in this case, we have 2A on the right, 2A on the left. We've got C on the right, and we've got C on the left. Okay, so it asks us if there are any intermediates. Well, an intermediate, again, is produced and consumed in the reaction. Okay, so 2A is definitely an intermediate. And C is as well. Okay, so we have actually 2 intermediates here. Okay, what is the rate law and order of each step? Okay, now in each step, you can leave the intermediates, okay? So we don't have to worry about substitution. We only worry about the substitution for our final rate law. Okay, so for this one, our rate law for number 1, and I'll just call it R1, is equal to, we'll just call this K1 times concentration of A2. Okay, so for R1, this would obviously be first order. Okay, looking at R2, we would write our rate law. Remember, we only look at the reactants and we raise the concentration to whatever the coefficients are for each of the elementary steps. So we'll put K2 here. Okay, A is going to be raised to that second power because of the coefficient, and B is going to be raised to the first power. You add up the coefficient, the superscripts, exponents. 2 plus 1 is 3, so this one is third order. Okay. And then for step 3, okay, rate 3 is going to equal K3 times the concentration of C times the concentration of D, and this is obviously second order. Let me know if you have any questions on anything so far. So we just did the rate law in order of each elementary step. What species can appear in the final rate law? Okay, well, it has to be the reactants that are in the overall equation. Okay, in our overall equation, what's left, I'm going to just underline what's left in red, would be A2, okay, plus B plus D yields E. So these would be the only, if they're asking for the actual species, it would be A2, B, or actually it would just be A2 and B because of the rate determining step. Okay, but if they're asking generally, A2, B, or D could have gone in if we had a substitute or something. Okay, is the following rate law consistent with the above data? Okay, well, let's look. Let me copy this to another page Let me see if I can just copy it. Okay, there we go. Okay, so let's, I'm going to just get rid of a couple things on this page. I have some more room. Okay, so remember, let's write the rate law. We're going to write it based off of rate, reaction. Oh, I'm actually substitute. Oops. One, two, three. Okay, so for the slow step, we're going to write our rate law. That's going to be R2 equals K2 A squared B. A squared B. Okay, now just make sure I'm doing something right. I feel like I'm missing something. Oh, no, I'm not. Okay, but we determined that in the last thing that A and C were our intermediates. So let's circle them. Okay, so that means we have to substitute for A. We can't leave that in our final rate equation. Okay, but what we learned yesterday is if we have an equilibrium equation that's fast, we know that for equation 1, we know that the rate of the forward reaction equals the rate of the reverse. Okay, and so for the rate of the forward, okay, the rate would equal K, we'll call it K1 times A sub 2. And that's going to equal the rate of the reverse, okay, which would be going this direction, which equals okay, we're going to call the K just the inverse. So we'll call that K negative 1 times A squared. Okay, good news is that we have A squared up here and A squared here, so we don't have to do any square roots or anything. Okay, so we can just substitute directly. Okay, so what we're going to do is divide both sides by this reaction rate for the reverse reaction, cancels it out. And now we have a substitution for A squared. Okay, so now let's substitute and write our final rate. So we're going to bring this down here. So R2 is going to equal K2. Okay, now we're going to substitute all this K1, A2 over K negative 1, and then of course times B. Okay, so this is all our substituted value for A squared. Okay, now remember we could take all these K's here, we make them big K, so we're just going to make it big K. And then our rate's going to be equal to, we'll write our final thing, big K, A2 times B. Okay, and that, the question in the problem asked, is this consistent with your data? Okay, and the answer is yes, this rate law is consistent with the data. Okay, so let's practice again. All right, now this is an actual equation, excuse me, a set of reaction. This is an actual problem. Okay, so it says the following mechanism is proposed for the reaction of methane gas with chlorine gas. Okay, is CH3Cl a catalyst or an intermediate? Justify. Then identify the order of reaction with respect to methane and chlorine. All right, so take a look at that. I'm going to pause the video again, and I want you to look at that and see if you can figure this out. So the first thing I'm going to do is just make this a little smaller so I can do that. So just so I have more room. Okay, so the first thing is CH3Cl a catalyst or an intermediate? Okay, so first of all, let's look and see our reactions here. We got a fast equilibrium, we got some slow, and some fast. Okay, so let's see, we're looking at this. Okay, so I can write the overall reaction, but what I can do is I am going to start looking at things that, let's just look at this one first because there's a lot here. Okay, so I've underlined what they've asked for, a CH3Cl. What I can see is it's not in the original reactant, okay, and it's going to cancel out. So it is going to be, the answer is going to be an intermediate because it's produced and consumed. If it was a catalyst, it would be at the beginning and it would show up at the end. So it's a intermediate because it was produced and consumed. Okay, then they want to know, the second problem is to know the order of reaction with respect to methane and chlorine, Cl2. Okay. So the first thing I'm going to do is everything is numbered 1, 2, 3, 4, 5. I know that I am going to rate my equation based off of step 2. Okay, so step 2 is going to write R2 equals K2, and then I have methane, CH4, and Cl. Okay, now, if you look at Cl though, okay, not Cl2, okay, you can see that Cl ends up being an intermediate as well, okay? Cl pops up and then gets canceled several times in the problem. Let me just make sure. Yes. Okay, so if you add it all up, you have 3 chlorines on the right and 3 chlorines on the left. Okay, so they cancel out. So chlorine is another one that is an intermediate. Okay, it gets produced and consumed like twice. Okay, which means in my final rate law, I can't have chlorine. I got to substitute for chlorine. Okay, if you look, you'll end up with methane. That'll be in your final rate law, in your overall reaction, but chlorine will not. Okay, so I circled everything that's going to be in the final. This is where it's nice to have different color pens, kind of figure out what gets canceled out and what remains. Okay, so I circled in blue everything that's going to stay in my final overall reaction. So that's in blue. Okay, and chlorine is not one of them. So I have to look at my equilibrium principle. So now I'm going to look at rate 1 because it's fast equilibrium. Okay, so I know rate 1. Okay, I know the rate of the forward is going to equal the rate of the reverse. Okay, and for the forward, I'm going to call that K1 times the concentration of Cl2, which is going to equal the reverse, which I'm going to call K negative 1 for the rate constant, Cl squared. Okay. Now, I got to substitute for Cl, not Cl squared. Okay, so what I'm going to do is, first thing I'm going to do is divide by k negative 1 over here, and that gets rid of this. And then I'm going to take the square root of both sides. Okay, and I'm going to write it instead as Cl2 to the 1/2 instead of writing square root. And that's going to equal Cl. Okay, so now I am going to substitute this monster with this. Okay, so let's write it again. Okay, so now we've got K2. I'm going to write my substitution. I'll write CH4 in here. Okay, and I'm going to write all my substitution in green. Okay, and now I'm going to simplify it. Remember what I do. I take my K's. I'm going to make it big K. Okay, so I'm going to come down here and write it so we have more space. But I'm going to write my rate equals big K times CH4 times Cl2 to the 1/2. And this would be my final rate equation. So that means identifying the order. That's not what they asked. They said, what's the order of methane? Okay, so methane would be first order. And chlorine would be top order. Okay, and that would be your answer. Okay, that was a little tricky. Okay. Now we have another problem here. I think I'm going to use this as a warm-up for tomorrow, so we're just going to skip that for now, and we're going to get into the rest of the lesson. Okay, so now we're going to talk about what it takes, okay, to actually have a reaction. Okay, you see the equations, you see the mechanisms, you see the elementary steps. But what actually physically happens to make a chemical reaction happen? Okay, and collision theory explains that. Okay, so with a reaction, it requires the actual collision between particles. There's no collision, there's no reaction. Okay, not all collisions will result in a reaction. Okay, so the energy, the total energy of motion, the kinetic energy of these particles has to be greater than what's called the activation energy. Activation energy is the minimum amount of energy needed to create the reaction. So there's 2 points. Activation energy is needed. It's got to be higher than the activation energy, equal to or higher than. And then the orientation of these molecules must be correct. I think of it, when I picture it, I think of it like a puzzle. Like, think about 2 puzzle pieces when you put them together, right? Jigsaw puzzle. You can't turn them every way. And it's the same thing with these 2 molecules that collide. They have to hit in the right orientation, or they're not going to break bonds and make new bonds. Okay, and it depends, of course, on their shape, right? Some puzzle pieces fit a certain way, top to bottom, some fit sideways. Okay, so those are the 2 requirements: enough kinetic energy of the particles, and the orientation has to be correct. Okay, the middle of the reaction is called the transition state. We used to call the actual place where not used to, we still do in honors, where the bonds are breaking and new bonds are formed, we called that the activated complex. This is that high energy place where bonds are breaking and new bonds are formed. It's kind of a transition state. Okay, so the last couple things on the slide tell you that the total kinetic energy of the reactant must be as high as the activation energy. And the transition state does not always proceed to the products, okay? There could be several transition states, and that's what we're going to look at. Okay, so let's just look at actual physical collisions. Okay, look at number 1 here. Okay, these reactants are moving too slow. So look, nothing happens, they bounce off. Okay, these reactants aren't facing the right way. You can see that the blue's facing, but now the red's facing. Okay, so they're going to bounce. Here, we've got our good reaction. We've got them moving fast and with enough energy, enough kinetic energy, and they're oriented the right way. So there's going to be a reaction. Okay, so again, when we talked about this is a bimolecular reaction, right? 2 molecules. Think about 3 molecules. That's why we talked about termolecular being rare. For 3 molecules to actually go through with the reaction, have enough energy, and hit at the right spot, it's like 3 puzzle pieces having to fit. The more puzzle pieces you have, the less likely they're going to fit if you throw them at each other. Okay. Now let's talk about what's called the reaction energy profile. We talked about this in honors as called the potential energy diagram. Okay, but this is one that we looked at honors. Let me see if I can make this a little bigger. It's a little small. Well, we'll just see if we can take a look at it. Okay, so you can see that on your y-axis, you have potential energy, right? Energy that's stored. On your x-axis, you just really have the progress of the reaction. So it's like moving from reactants to products. Okay. On the left side here, you have your reactants, and you can see they have a certain amount of potential energy they start with. All right, and you can see the products after they're done have some energy too. Okay, so when we were in honors, I used to call this the heat of the reactants, which was like the energy of the reactants, and over here was the energy of the products. Then we calculated the enthalpy of the reaction, which would be the products. It was always the same formula, products minus reactants. And obviously this is for the forward reaction, which is going from left to right. Now at the very top here, this is the activated complex. So that activated complex or transition state has a certain amount of energy. We used to use a symbol with an equal sign and a slash for the activated complex. And you can see it has a real high energy up there. That transition state's where bonds are breaking and new bonds are formed. Okay, so that's the activated complex. Now, make sure you understand that the heat of the reaction, or delta H, has no effect on the reaction rate. Okay? The rate only depends on the size of the activation energy. Okay, that's the energy required for the reactants to collide in the right orientation. And that's measured right here. It's the energy from the reactants to the peak. That's called the activation energy. Okay, so it's the energy required, the minimum energy required if they're in the right orientation for a reaction to occur. And you measure it from the reactant's energy all the way up to the activated complex. And again, what I've been measuring so far is all for the forward reaction. Okay, now the reverse reaction, you would just reverse it, okay? they would be the same total energy. One would be exothermic, one would be endothermic. Okay, so let's look at a couple more that have exothermic and endothermic so you can see. Okay, so remember, endothermic means energy has to be put into the system. Okay, you can see here in this first, this is an endothermic reaction and this is an exo. Okay, now if you can't see it, remember delta H, which is the enthalpy of the reaction, is going to be the products minus the reactants. Okay, here it looks like the products are 225 and the reactants are at 75, which is going to give you a positive number. Positive number tells you it's endothermic. Energy is being put into the system. Here on the right side, you have, let's just call this, we'll just say this is 4 and this is 8. Okay, so if you're doing your delta H, it's going to be 4 kilojoules minus 8, which is going to be a negative 4. Okay, so you can see that this reaction on the right is exothermic. The products are lower than the reactants. Still got a positive activation energy though. Oops, okay, so there's your activation energy in both. Okay. Now let's talk about this related to reaction mechanism. Okay, so think about all those different elementary steps. This is just showing you one step with one activation energy. But what about these rate mechanisms? The one with the elementary steps. Okay, why is the slow step the slow step? Because every reaction requires the right collisions, effective collisions, right orientation, enough activation energy. This step with the largest activation energy is the rate determining step. Okay, meaning the highest peak. Okay, the highest difference between the reactants and that activated complex is going to be your rate determining step. And you can look at a potential energy diagram and see that. Okay, so here we got more potential energies now. But now we've got like a bunch of humps. It looks like a camel. All right. So you can see here, this is a multi-step process. You got multiple activated complex, multiple activation energies. Let's just look at the left one. Okay, so here's your energy of the reactants. Okay, here's one of the activation energies here. Here's a second. Okay, so, and then here's a third. Oh gosh. Okay, so everything that I just outlined is activation energy for the 3 elementary steps. If you had to look at this, which is like a very typical AP problem, and say which of these 3 is the rate determining step? 1, 1, 2, or 3, okay, you would answer 3 because it has the highest activation energy. The one with the highest activation energy is going to be your rate determining step. Okay, so here's another problem and they could also ask you the problem, okay, in number 1 over here. Okay, in number 1 over here, how many elementary steps are in this part of this rate mechanism? And literally you would count the little hills. 1, 2, 3. This would be a 3-step reaction in the left side. In the right, it would be a 2-step. Okay, but you would say if they asked you which one is the rate determining step, you would have to look at the activation energies, and the first one having the highest activation energy would be the rate determining step. The one with the highest activation energy is the rate determining step. Okay. Now, I want to talk the last section in the last bullet in the AP curriculum for this unit is to talk about catalysts. Okay, so I want to talk about them and make sure you understand what a catalyst is, what it does, and what it does not do. Okay, so that's important. Okay, so the first thing I want to talk about is that a catalyst is used to speed up a reaction. Okay, and it's actually not used. What it means when it says without being used, it means it's not used in the chemical reaction. It's not a part of the reaction. It shows up at the beginning and it shows up at the end. It's not used up. All right. It allows the reactions to proceed with a new pathway. This is really important. It gives them like an alternative pathway, a new or alternative pathway with a lower activation energy. Okay. A new mechanism. Now this is important right here, very important. It does not affect the overall energy of the reaction. Does not change anything about the total energy used in the reaction, only that activation energy. It lowers it. Now here is a potential energy diagram that's catalyzed and uncatalyzed. Okay, it's just a one-stepper. Okay, an enzyme you probably learned in biology is a type of catalyst. I don't know a lot about enzymes except they're catalysts. Anyway, you can see here, if you look at the activation energy of the catalyzed reaction, which is the blue, here's our activation energy, E sub A. And then if I wrote in the activation energy without the enzyme, you can see that the activation energy is much lower. But notice the products don't change where they are. What is going on? This must be like a link. The reactants, the energy of the products don't change. The energy of the reactants don't change. The total delta H doesn't change. Only the activation energy. It gives it an alternative path, an alternative mechanism. Okay. So let's look at this problem together. Okay. I'm going to pause the video and I want you to see if you can do this yourself. Okay, and then we'll go over it. All right, so in this you have 4 diagrams, and this would be a free response. This is an actual AP exam free response. Identify the 2 diagrams that could represent a catalyzed and an uncatalyzed reaction pathway for the same reaction. Indicate which of the 2 diagrams represent the catalyzed pathway for the reaction. Okay, so in this case, you first have to decide which ones are the same reaction, which means they have to have the same total enthalpy. And the only 2 that do that are these 2 here. The other 2 are completely different reactions. You can see that the energy of the products is the same as the energy of the reactants in both diagram 1 and 2. Okay, and then the second part would be to identify the one that would be the catalyzed. Okay, well, catalyzed means it's going to lower the reaction pathway. So diagram 1 would be your answer for the catalyzed. Okay. Now the next part could be a little challenging. Okay, I always find these things a little challenging. Indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. Okay, so the statement is, adding a catalyst to a reaction mixture adds energy that causes the reaction to proceed more quickly? Okay, well, the answer is actually disagree. So you should say disagree. And the reason you're saying is the catalyst does not add energy. It provides an alternate pathway, okay, by lowering the activation energy. So it does not add energy, because remember, delta H does not change. Okay, so delta H does not change. So this is incorrect. It does not add energy. All it does is add an alternate pathway, and that would be your explanation. So the answer should be disagree, and it provides an alternate pathway. And you could say something about lowering the activation energy as well. Okay, so let's finish this unit. Okay, and then I want you to, we're going to watch a little video, an AP video just on the two types of catalysts to make sure you kind of understand how they work. And I'd like you to take notes when we watch it. So I'll give you a minute to, get your stuff together. Okay, so Maxwell-Boltzmann graph. Okay, we've seen one of these before where they have speed on the x-axis, number of molecules on the y-axis. And remember, the area under the curve has to be the same for all three lines because we're talking about the same number of molecules. All right, so remember, as you increase temperature, okay, you have more molecules at a higher speed. Okay. Now, it's very important to understand, though, that temperature does not change that activation energy. It changes the kinetic energy. So not the activation energy, just the kinetic energy. Okay. So this is just showing you a graph, okay, where same type of graph, okay, so we have low temperature in blue, high temperature in red, area under the curve the same number of molecules, okay, and then they marked with this vertical blue line where that minimum energy is. Okay, now it doesn't change at a higher temperature, but what it does is show you that there are more molecules that can get to that energy. Okay, so what it does, it doesn't change where that activation energy is. Okay, that activation energy is the same, but as you increase the temperature, you increase the number of molecules that can meet the activation energy requirements. Okay, so what does increased kinetic energy mean for rate? Okay, increased temperature means increased kinetic energy, means you have more effective collisions. More particles have that high energy. Okay. Incorporated into the rate law. Well, there's a rate law right there. And it turns out that temperature affects K, the rate constant. It's the only thing that changes K. Only temperature, not concentration of anything. It's just temperature. Okay, so this is an equation. We're not going to use it really. Okay, but it's called the Arrhenius equation. Okay, and you can see it's comparing two rates at two different, rate constants at two different temperatures. Okay, so you have in this equation, again, I've never seen a problem where we actually use it, but you have the activation energy, which doesn't change with temperature in joules. Your R is your 8.314 value, okay, which is on your AP Chem sheet. And then, of course, you have two different temperatures and two different rate constants. All right, so if the moral of the story is, if you increase the temperature by 10 degrees, it will double the rate of reaction. Okay, that's kind of what that equation ends up proving to you. Okay, now, what we're going to do in the last 15 minutes, that sheet I gave you is not going to take you really a long time, is we're going to talk about the two types of catalysts. Okay, there's a homogeneous catalyst and a heterogeneous. Homogeneous and heterogeneous. Now, homo, of course, means same, hetero means many. The key is the catalyst is in the same phase as your components of the reaction. So, for example, if you had, say you're doing some aqueous reaction, the catalyst would be an aqueous solution as well. Okay, heterogeneous means it's at a different phase. Okay, so for example, they have these solid catalysts. Okay, where you have the catalyst surface, and this is like a metal, say platinum. And then you have gas particles that are reacting on the surface of the catalyst. Okay, so this would be a gas. So heterogeneous catalyst means different phase. So a lot of times they'll use a solid catalyst with like gas particles. So that's the two different ones. Okay, so what I want to do now, I'm going to stop the video.